So, we'll start. Well, let me just take this real quick. Yeah, and we'll save it, and then we'll put it 1. I gotta delete the other ones that I have in here later. All right. Or yeah, okay. So I'll open up 1, and then I'll Control A. That did not do anything. Wait. There we go. Now it's copied, and then we can Control N, and we'll do this. This one works. Okay. Alright, I'll make this a little bit bigger. So basically, what we're doing is so we're finding like the derivative, or like if we were to graph the derivative of this graph, we're finding what like these values on that graph would be. So what the derivative is it's the slope. So like, for example, this the answer to this would be the whatever the slope is at or it would be whatever the slope is at -3 on this graph. And so originally I was confused because because it gives us points, right? And so we have a point here at -3, 0, and we have a point here at -1, 2. And so, you can do -3, 0, -1, 2. And so at these points, you can do y2 minus y1 over x2 minus x1, and you can get 2 over 2, and so you'd have a slope of 1. However, that would be if this were linear, which would look more like this than this. This slope is constantly changing, which means that we can use the fact that the slope of the linear line between these 2 points is 1. We can use that to kind of figure out what the slope here would be, but we don't really know what it is necessarily. So I would say, because as this graph goes out, you can kind of tell it starts to go downward more, right? Like, you expect it to go downward more, which means that the slope is greater on this side than it is over here, because over here it starts to plateau a bit until it reaches 0, and then the slope is 0. Which is why at the curves here, or the bumps, it's the derivative is always going to be 0. So because we know that, and actually we could graph this. We know the slope is positive because it's going up as you go farther right, and we know it's getting greater over time. So it's becoming less over time. My apologies. So we know it would look something like this. And with that information, we know that, and it just wants us to approximate the answer. We don't need a foolproof answer. But with that information, we know that the slope is of at -3 is gonna be about 1.5, which 1.5, which I'm just judging based off of the graph that I drew here. Another way to do this is you can look at this point here and you can approximate what this point is, because this because basically you draw between these 2 points and you have a linear line, meaning the slope you get for here is probably going to be the answer. I'm not 100% sure this will work, but I'm fairly confident. So you have y1 at, I'd say, -3.5, -1, or you have you have 0.1, and you have 0.2 at -3, 0, and then you do y2 minus y1 over x2 should be -3 minus x1, and you get 1 over 0.5. Yeah, 1 over 0.5, which should be 2. So you get a slope about 2. And it's not the same answer. I'm pretty sure on the answer key, the actual slope, on the answer key, the actual slope is 1.5. So, you could make the argument that the graph of the derivative that you draw here would probably be a more accurate way to do this, especially since the slope here is changing. The slope is 2 because, like I said, it gets greater over time. So even though this line right here looks pretty linear, it's still changing. But I'm sure if you put 2 with your answer, it would still be considered right because these are approximations. So, and I'll do another example, just to prove to myself and just to, help, just to prove to myself that this theory works, but also, and I'm out of, all right, let's just, no, not that one. What? No, okay. I hate you a lot. This one. There we go. Alright. So, we'll just do another example. So we have, we'll do f of 0. And we give this a point at f of 0. It gives us a point here as well, and a point here. So what we can do is we can judge that the right here there's a bump, and here's a bump, and right here is a bump. And actually I need to, and I'm gonna do this in black. Right here there's a bump, and right here is a bump. Now, basically we need to judge what the slope is doing. So right here we can say that there's a negative slope because the slope is going down as it goes farther right, meaning that the graph of the derivative we draw is going to be below the y-axis. And then it's going to be negative the whole time, but it's also going to be a decreasing slope, or it's going to be getting closer to 0, meaning it's technically going to be an increasing slope. Like, the slope is going to be increasing over time because it's negative, meaning that the closer it gets to 0, the more it's increasing. But basically, I would imagine it's probably going to look something like this. So, and hang on, I want to make sure this is accurate. Okay. So I realized, I'm not entirely sure like how this slope is going to, how this graph is going to look like. I don't know how far down it'll go. I'm not sure how inaccurate our approximations are supposed to be either. But I would say that a way to check your answer is to use the points that it gives you on the graph. So, we have right here, we have -1, 2, and we have 0, 0. Okay, 0, 0, and we have 1, -2. So obviously, if we were to draw this line, okay, and that. I want to draw. Is there a tool that lets me draw a straight line? Okay, but it would look kind of like this, except straighter. So you can see that the slope is different over time. I'd say so. How it's supposed to be, I would say that around like here, around where the 0 is, around here, the slope is probably at its lowest point. At its lowest point, or like at its it's at its greatest, you could say, like the incline of the graph. If you were to put the ruler here, I feel like you'd have to move it farther, like more inclined downward around this area than here or here, because here is where it starts to flatten out again, whereas here it's starting to point downward until it stops pointing downward, which means I believe that the 0 is probably going to be around like the lowest point on the derivative graph, at least for this, between these 2 points. And so knowing this, we just have to calculate the slope, and I'm pretty sure the slope is going to be the same between these. We just have to calculate the slope between these 3 points. We start here, we go down 2, we go over 1, so should be -2, and then here we go down 2, we go over 1, this is also -2. So basically, I would say that the slope right here, because like you could kind of say this is like an average slope for the graph, is -2, because, or at least this section of the graph, I mean, meaning, and since the 0 is like kind of like the peak, like right here, we showed that it touches down here, I would do something below -2. So I would do -3. The answer on the answer key is -4, I believe. Yeah. So I would do something like that. It's frustrating to have to make approximations like that, but that's in general just how you're gonna get by with this. Is you just compare it to like the average slope, like what the slope would be if it were linear, and then you kind of compare it to where it is in the graph. So like here, it has the farthest incline compared to like here, where it flattens out a little bit, and here where it also starts to flatten out a little bit. So you know that it's probably gonna have a slower slope, or a slope that's more inclined down this way than the average slope, but like between these 2 lines. And because that average slope is -2, I just chose -3. And I'll do one more. I don't know if you'll need it, and I don't know how helpful this has been so far, but I'll do one more. 1 second. So the derivative at 3. Again, I'm just gonna do what I did with the slopes. So we give us a point here at 1, -2, and it gives us a point here at 3, 0. You don't really have to plug it into the y2 minus y1 over x2 minus x1. You can just kind of go 1, 2, 3, or no, sorry, 1, 2, and then 1, 2. So we know that the slope of, this line right here, we know that this slope is going to be 1, because it's 2 over 2. So now comparatively, the slope is going to be more, like it's going to be flatter over here, which means that the slope is greater at this part of the graph, which you can see because it starts to go up. Now, if we were to graph, so we know so far that the slope is going to be greater than 1. It's going to be about greater than 1, or about greater than 1. It's going to be greater than 1. So a number that's like a little bit greater than 1, you can use 2. But just to prove a point, we can also graph this. I tried that last time. It wasn't as effective, but still. So we have a curve, a bump here. So we do this. And the slope is positive going this way. So it's going to be going this way. And it's increasing over time as well. So this is going to be a positive slope of the derivative. And it's going to be above the x-axis. And it's gonna be about like here. So at this point, it's about like 2.5. So I would use 2.5. I think 2.5 is a pretty safe answer. Let's see what it says in the answer key. On the answer key, it's 1.5. I would say like 1.5 to 2.5 is pretty safe. And I'm not 100% sure about these methods. This is just how I chose to solve these, and it says in the directions to use a given graph to estimate keyword the value of each derivative. I'm sure we get quite a bit of leeway for that, and also this is not on the test. I mean, I didn't see it on the test at the very least, so I don't really think this is like, just don't worry about this too much. Just use these methods. It's obviously it's going to be a little bit inaccurate because all of these have been inaccurate so far, except for my answer for -3. But I would just use the method where you calculate the slope, and then like here and here, here to here, and then which here it's 1, and then basically you figure out between these points what the slope of the graph of the actual graph, not the fake linear graph I just made, but what the slope of the actual graph is, like at the point you're finding. So like this is 3, right? And at 3 you're at like the end of it, and it's starting to go up more, so it's like it's basically gonna be above this 1, right? Because right here it's 1, and it's already starting to increase at like here. So you could think of it as 1 is like the average slope between these areas. Right here is where it starts to plateau more, and it's going to be lower than 1. But right here is where it starts to, it starts to like increase more, and it starts to go up, meaning it's going to be greater than 1. And the answer that is in the answer key is 1.5. I'd say, yeah, 1.5 to 2.5. You might generally be able to just get away with going 1.5 or 0.5 more or less than what this average is, like depending on if it's like greater than or less than that average. Like right here at 1, I think the slope you could probably say is actually no, the slope at 1 is 0. We know that, right? Let me make sure that's true. Yeah, the slope at 1 is 0 because it's a hill, it's a bump. So we know at the bumps it's going to be 0, but other than that, and this is ask about -1, yeah, right here is also 0. -1 and -1, those are kind of guaranteed answers that we need to know. 0. Yeah, I hope this helped. If it didn't, let me know. I'll try to figure out a different way to explain that. But don't worry about this too much. Don't worry about it being inaccurate, because it says to estimate, and don't worry about the test, because I don't think it's on the test. Okay. And also, I'm not 100% sure it's done on the test, but I had the third sheet. I didn't see anything like that, but I didn't read the entire back. So, okay. Yeah. Good luck. This is an 18-minute video. Oh, no.